Hey y'all. In the last video, we looked at how to determine the predicted rate law for a mechanism when the step that is first is the rate determining step. In today's video, we're going to complicate things by looking at what happens when the second or later steps are in fact the rate determining steps. There are really two techniques to do this. I'm going to first show you the longer form technique. And the reason I'm going to show you that first is because it works every time. I will then show you what I call the Quickie method. And that works, I would say, probably about 90 to 95% of the time, which means it's really helpful because it's much, much faster, but it could also get you in a pickle if you don't know when and how to use it. So we're going to start by looking at what I call the equilibrium method. Let's start by looking at a reaction and its experimental rate law. Now, in the reaction we're looking at here, we take two nitrogen monoxides, combine it with a bromine, Br2, and we get two NOBRs. Now, the data shows that the rate law of this experiment was second order with respect to the nitrogen monoxide and first order with respect to bromine. So we might think, hey, one step, no big deal. But remember, three molecules colliding at one place at one time with sufficient orientation and energy to overcome the activation energy is extremely rare and slow, and quite frankly, unlikely. So we're going to propose a mechanism. And in this proposed mechanism, I propose that the first step is fast and the second step is slow. So in the first step, we combine nitrogen monoxide with a bromine. And in the second step, we combine nitrogen monoxide with NOBR2, which is, in this case, an intermediate. So these are my two steps, and you'll see that the slow step I've proposed is second. Now remember, mechanisms are proposed. You don't have to come up with these off the top of your head. You're going to be given the fundamental skeleton of any mechanism that you're going to be asked about. And in almost every circumstance, you're going to be told which one was proposed as the fast or the slow step. And if you're not told that, you'll be given enough information to determine on your own which one is fast or slow. In this case, the slow step we've proposed is second. So how do we determine the rate law for this mechanism? Well, the first thing we need to do is understand that in any mechanism, we have to account for everything up until the arrow of the slow step. That means the first step does play a role in the rate, but it's fast, and the second one is slower. So what ends up happening is over time, the first step is going to happen faster and start building up products. Now, in the case that the first step is reversible, which means it can go in both directions, and many reactions are reversible, what's going to happen is the first step is going to reach a state of equilibrium. Now, we haven't talked about equilibrium yet this year, but equilibrium means that the rate of the reaction in the forward direction is equal to the rate of the reaction in the reverse direction. So the reaction keeps going in both directions and at the same rate. This is important to understand. The second step still controls the overall rate, but the first step doesn't stop. It's still happening. It's happening in the forward direction and the reverse direction. So what I'm going to do is write the rate law for the first step, the elementary step, in the forward direction. But I'm also going to write the rate law for that first step in the reverse. Okay? So if we think about the reverse, the NOBR2 is in fact the reactant in the reverse direction. In the forward direction, it's NO and Br2. Now, we just said that the first step being at that state of equilibrium means the rate of the forward elementary step is equal to the rate of the reverse. So we're actually going to set those two equal to each other, which means that K of the first step in the forward direction, lowercase k, remember this is rate law, so there's a lowercase k, times the concentration of the NO times the concentration of the Br2 is equal to K of the first step in reverse, which is a different K value. Okay, it's not the same K value, it's a different K value. So I'm going to do a subscript K1 reverse times the concentration of NOBr2. Why are we doing this? Well, both of these reactions are happening. at rates, and those rates are equal. The reason we're doing this, though, is because that second step, the rate determining step, has NOBR2 in it. That's an intermediate. Now, in most circumstances, we do not have the capacity or ability to include intermediates in rate laws. It's much easier to include the reactants in rate laws. This requires what's called an approximation, sometimes known as the steady state approximation, depending on the circumstance. But these approximations estimate rate laws. They're not perfect, admittedly, but they do a pretty decent job of getting around the ballpark of the rate law using experimental data of just initial concentrations of reactants. And that's what we're looking at here. So if we look at removing that intermediate from the rate law of the elementary second elementary step, the way we can do this is with substitution. We're going to solve for the concentration of NOBR2 in that first series of equations. And we're going to substitute in to the second elementary steps rate law. Now, admittedly, this looks ugly. Notice how when we substitute in K1 forward over K1 reverse times NO times BR2, and then you substitute that in for NOBR2, and it gets kind of messy because it's K2 times K1 over K1 reverse times NO times BR2 times NO. Like, that's complicated. Can I tell you a trick, though? Those K values, well, they all combine into one. We'll call it K observed. And the reason they combine into one is because each of those K values is a component of the overall reaction. Each one represents a synthesis of activation energies and other variables associated with the rates of each elementary step. And they all combine into one K value that we observe for the overall reaction. So what I'm going to do is I'm going to take all those K values and summarize them and condense them into one K value. And we can do that because they're all combining to that one K value in reality anyways. So when I look at the overall mechanism's rate law, I have determined it by first setting the reaction of the elementary step, the first elementary step, forward and reverse equal to each other, substituting in to the rate law of the second elementary step, which is the rate determining step in this case, and then finding the rate. And if you look at this, when we combine the NOs, you will see that the experimental rate law, second order with respect to NO, first order with respect to BR2, is equal to the predicted rate law of this mechanism. So when the second step is slow, the equilibrium method, which works every time using a series of substitution and systems of equations, we can find the rate law for the proposed mechanism. That took a little bit of time, though. So there's got to be a quicker way, and there is. Can I show you the quicker way? And let me tell you right now, I'm going to tell you the quicker way, and then I'm going to tell you when the quick way doesn't work. So the quicker way is this. All we do is ignore the arrow after the slow step, okay? So we take the arrow from the slow step and ignore everything after that. Any intermediates, cancel. And then add up everything else. So if we do this, you'll notice that we've ignored everything after the arrow of the slow step. We've canceled the NOBR2 intermediate, and we're left with 2 NOs and 1 BR2. So it's second order with respect to NO and first order with respect to BR2. That's the Quickie method. That's the quicker way of determining the rate order of a mechanism. But it doesn't work every time. Because remember that thing I said where you have to cancel your intermediates? What happens if an intermediate doesn't cancel until after the arrow of the slow step? What if we have 3 steps and the intermediate's formed as a product of the first step and then only used as a reactant in the third step, but the second step determines the rate? There's no way to use the Quickie method in order to solve for this. Also, it gets more complicated if our rate orders happen to be fractions or negatives. The experimental data might not look pretty. The equilibrium method works for those circumstances, so you should practice it. But especially in a multiple choice type situation, the quicker method works very well, and it does work 90 to 95% of the time. So it's good to have in your back pocket. So when we're looking at determining the validity of mechanisms, figuring out whether the reaction's first step or a subsequent step or the rate determining step makes all the difference. If the first step is the rate determining step, easy. If the rate determining step is second or later, it gets more complicated. You need to make sure you know when you can use the quicker method versus the equilibrium method. And if you use the equilibrium method, you need to make sure that you're doing your math properly, substituting in properly, and solving properly. So that wraps up today's video. Today we looked at the way we solve for the rate law of a mechanism if the second or a later step is the rate determining step. I hope you enjoyed this video, and I'll see you in the next one.